Okay, so in this video, we'll consider three special examples of discrete random variables. The first one is the simplest one, called a Bernoulli random variable or a Bernoulli experiment. So what is the experiment? The experiment actually is very simple. It is one trial that can result either in a success or in a failure. So you have an experiment where there's only two possible outcomes. The best example of this would be flipping a coin. If you think of the two possible outcomes, well, the coin will either land on heads or on tails. So there are only two outcomes, heads and tails, and the event that is a success is whichever event you're interested in. So suppose you say you win something if the coin lands on, let's say, heads, then heads you'd consider a success. And by default, the other outcome, tails, would be considered a failure. And now you ask, well, what is our random variable? So you perform the experiment once and only once. So you flip the coin, heads or tails. If you get heads, you have a success. If you land on tails, you have a failure. And x is simply the number of successes. So if you think of the possible values of x, since there's only one trial, well, if the coin lands on tails, that's a failure, hence no success. X is equal to 0. Or the only other possibility is the coin landing on heads would give you one success. So x is either equal to 0, 1. If x is 0, you have no success, therefore a unique failure. If x is 1, you have one success. Well, the probability of a failure is the probability that x equals 0, since x is the number of successes. And this we usually denote as Q. The probability that x equals 1, the probability of observing a success, is denoted by P, and that is the only parameter of this distribution. So we write x squiggly line Bernoulli to say that x is a random variable that follows the Bernoulli distribution, and there is only one parameter. In the Bernoulli experiment, since there's only one trial, we have to give the probability of success, and that is equal to P. And of course, by default, Q is the probability of failure. But since we only have a success or a failure, then Q is simply 1 minus P. So in our example, if we assume that the coin was fair, the probability of a failure, which would be getting tails, would be 1/2. And the probability of a success, that the coin lands on heads, would be equal to also 1/2. The coin could be biased, and we may have different values than 1/2 and 1/2. It could be 0.4 and 0.6. And that's it. So a single trial that results in either a success or a failure. So there are only two possible outcomes, and whichever outcome you are interested in, this will be the outcome that will become a success. The only questions left over is, in this case of a random variable, what is the average value and what is the variance? You can prove it from the definition. If you multiply and look for the mean, the expected value of x, remember that you multiply each value times its probability, so you would do 0 times Q plus 1 times P. So all you have in the end is the mean is equal to P. The average value is simply the probability of success. And the variance, if you compute it, sigma squared, happens to be simply P times Q. The probability of success times the probability of failure. Hence the deviation is the root of PQ. And that is the Bernoulli experiment. The next question is, what if we repeat the trial n number of times? So think of flipping the coin, and what if we say we don't flip the coin just once? What if we flip the coin 20 times? And we ask, how often will the coin land on heads, therefore of us observing a success. And this is what we call the binomial experiment. And again, all it is we repeat a Bernoulli experiment, so an experiment where we either observe success or failure, and we repeat this experiment several times, any number of times. And as before, x will be the total number of successes. So we will write x being the number of successes, and we will say that x follows a binomial distribution. And here there are two parameters. We have to specify how many times do we perform the experiment. So in this case, how many times do we flip a coin? Suppose we flip the coin n times. And we also have to specify for each trial what is the probability of success, hence p. So let's see how we can find the probability that x equals a given value using what we know of combinations. Right? So here, if you think of the values that are possible for x, if you perform, and we'll do it here, and trial. So you flip the coin, let's say you flip the coin n times. So you're going to have the first flip, the second flip, the third flip up to the nth and final flip. And if you think of it, well, okay, you flip the coin n times. Well, for us, a success, and again, a success is whatever you're interested in, the number of times we see heads, well, we may see heads never, and so we have 0 successes, or heads could appear only once, or exactly twice, or exactly 3 times, up to, well, we can't observe more than n successes since we only have n trials. So x ranges from 0 all the way up to n. And now a natural question is, what is the probability that the random variable, the total number of successes, equals a particular value for the number of successes? Well, if you think about it, the probability of success is p, and the probability of failure is q. So if you say there are x successes, that means a success and a success and a success x times. So it's p times p times p times p x times. Of course, that leaves n minus 1 because there are in total n trials. So that leaves, I'll write it here, there are n trials. So we flip the coin n times. So there are a total number of n flips. And if you have x successes, that leaves n minus x failures. So we're saying failure and failure and failure, n minus x times. The probability of each is q, so it's q times q times q times q, and minus x times, so it's q to the n minus x. Remember, q is simply 1 minus p. And now the only question is, well, in how many different ways can we observe n successes? Suppose, say, we observed 2 successes. So x was equal to 2. Well, out of these n possible flips, trials, which ones are the successes? So for example, I could say the second flip was a success, and the very last flip was a success. Or I could have a success first and second, or first and third, or fourth and fifth, and so on. So the idea here is quite simply, well, think of it this way. Suppose I say success in 2 and success in n, or I say success in n and success in 2. That's the exact same thing. So the order does not matter, and it is without replacement, right? If you say I have a success here and a success here again, that's still just one success. So out of these n trials, we have to choose our x successes. So out of the n given trials, we have to choose which of those n will actually be successes. So it's n choose x, the combination. Because it is without replacement, so we can't choose a trial twice, and the order does not matter. If I say again, the second flip is a success and the last one is a success, or I say the last one is a success and then the second one is, that's the same observation. And now you have the probability of observing this number of successes. So let's do an example. We could say that we flip the coin 10 times, and for us heads was a success, and we may ask, what is the probability that we observe, say, heads 7 times? So we flip the coin 10 times and we ask, what is the probability of flipping heads, of obtaining heads 7 times out of the 10 flips? Well, we're asking for the probability of x being equal to 7. And then we just use our formula. Out of the 10 flips, we choose our 7 successes times, if we assume the coin is fair, so 0.5, the probability of success, the probability of getting heads, 0.5, to the number of successes, 7, times the probability of failure, 0.5, if we assume once again the coin is fair, 2, and minus x. Well, n is the number of times we repeat the experiment, that's 10, minus 7 is 10 minus 7 is 3, and there you have it. If you compute this, so 10, choose 7, times 0.5, and here if you look at this one, it's 0.5 to the 10th power, you should find approximately 0.1172. So about 11.8% chances of observing 7 heads out of 10 consecutive flips. And that is the binomial experiment. The last thing worth mentioning here is what is the mean of this variable and what is the variance? Well, the mean is actually n times the probability of success, and the variance is actually equal to npq. And you may ask, well, how do we get this? We could go back to the definition of the mean and the variance, and we would find these two formulas. But we can do much simpler if we realize that the binomial experiment is simply a sum of Bernoulli random variables. Let's see how we can justify this claim. I give you n trials. So first, second, third, up to the nth trial. If x is binomial, n trials and p is the probability of success, n is the total number of successes, right? So you repeat the experiment n times and you ask, in these n trials, how often did I succeed? Well, think of it this way. What if I gave you now a list of n Bernoulli random variables? So I say x1, x2, up to xn. All of these are independent Bernoulli random variables with a probability of success being equal to p. Now think of it this way. Each Bernoulli random variable is equal to 0 if you have a failure, or 1 if you have a success. So think of now your sequence of n consecutive Bernoulli experiments. Think of flipping the coin. You flip the coin once. If you get heads, in our case that was a success, you add 1. If you get tails, you get 0, because that's a failure. But that is exactly what x1 is. x1 is a single binomial experiment. So x1 will be equal to 1 if you have a success. x1 will be 0 if you have a failure. So you add x1 plus, well, if your second trial is a success, you add 1. If it's a failure, you add 0. So you add x2. Because again, x2 will be 1 if you have a success, or 0 if you have a failure. Plus, and you keep like this, up to the nth trial. If the nth trial is a success, you add 1. If the nth trial is a failure, you add 0. But again, that's exactly what xn is. xn will be 1 if you have a success, and 0 if you have a failure. So you see a binomial experiment, a binomial random variable, with n trials is a sum of n independent Bernoulli random variables. Because if you want the total number of successes, for each trial, you add 1 if you have a success, or you add 0 if you have a failure. And that is exactly adding up the Bernoulli random variables. Why am I saying this? Because we know the mean for the Bernoulli and we know its variance. Right? For any Bernoulli, the expectation is simply p, and the variance is simply pq. Well, with the property of the expected value and the variance, e of x is the expectation of the sum but we're asking, what do we expect the sum to be? If the variables are independent, this will be what we expect x1 to be, plus what we expect x2 to be, up to what we expect xn to be. But each variable, x1, x2, up to xn, is a Bernoulli random variable, and the mean in each case is p. So all we have is p plus p plus p exactly n times. So all we have in the end is np. And that's why for a binomial random variable, the mean is simply np. And the same goes for the variance. If you ask now, well, what is the variance of x? Well, x is a sum of Bernoulli, so it's x1 plus x2 through xn. Well, the variance of a sum is the sum of the individual variances. So this will be variance of x1 plus variance of x2 up to variance of xn. But each variable here, x1, x2 through xn, is a Bernoulli random variable. And in each case, the variance is pq. So all we're going to have is pq plus pq plus pq, exactly once again n times. And so we're left with n pq. And that is the variance for the binomial random variable. Our last example will be the so-called Poisson random variable, and that's a slightly different random variable, but it's not very complicated. This is called the Poisson Experiment. So if you look at your notes on the Poisson experiment, what we have, and I won't write this down, but what you have is a fixed time interval, and over this time interval you observe the number of occurrences of a given event. And we write x, and x will be the actual number of occurrences And we usually write x is Poisson, since it follows this distribution. And there's only one parameter here, and we usually write lambda. This is the Greek letter L called lambda, written as L-M-A-B-D-A, lambda. And before we actually consider an example, just two short notes. A question is, what's the mean of a Poisson random variable? And the mean is simply lambda. That's what this parameter here is. And the variance is also lambda. Hence, the deviation is simply the square root of lambda. So consider an example. Oh, one last question is, well, how many observations could we have? Suppose we have the following example. You say, I'll stand by the road, and over a span of, let's say, 10 minutes, I'll count the number of black cars driving by. So x would be the number of times you see a black car over a span of 10 minutes. So you fix your time interval. So we go from 0 to 10 minutes. So you fix that. And then you say, well, how many black cars can I observe over 10 minutes? Well, maybe you'll observe none, maybe one, maybe two, maybe three. And here there's no real final limit. Depending on what you observe, x can take on larger and larger values. If you think of it, that's also dependent on your time interval. What if you have a time interval from 0 to 24 hours, or 0 to a month? Then the x values can be even larger. So there is no here upper bound for how large x can be. And if you ask, well, what's the probability that over a fixed time interval I observe this many occurrences of whichever event you're interested in? The answer is a little bit more complicated. It's e to the minus lambda, lambda to the x over x factorial. And the number e is the exponential at 1. And if you use your calculator and you compute e to the 1, you'll have approximately 2.71828. Now the number e is irrational, so it has an infinite decimal expansion. But it doesn't matter. In your calculator, you'll just use the command exp and then compute whichever value you have here. So suppose that in an example, we say over an interval of 10 minutes, from 0 to 10 minutes, suppose that on average, we observe 6 black cars. So lambda is your mean. So if on average we observe over the span of 10 minutes 6 black cars driving by, lambda equals 6. And we may ask, what's the probability that over a time interval from 0 to 10 minutes, the number of black cars we observe equals, say, 8? Well, we simply use our formula. It will be e to the negative lambda, where lambda is the average, so e to the negative 6, lambda to the x, so 6 to the number of successes, so of observations of the given event, so 6 to the 8, over 8 factorial. If you use your calculator to compute this, you'll have e to the negative 6 times 6 to the 8 divided by 6 factorial, 8 factorial, and you should find approximately 0.1033. So about 10%. So in that case, you would say over a fixed interval of 10 minutes, suppose you found the average number of black cars driving by to be 6, and you ask, what is the probability that I observe 8 black cars driving by over this interval of 10 minutes? It will be approximately 10.3%. And that is the Poisson random variable. In this case, we will not prove that these formulas hold. It's actually a little tricky from the probability distribution, so we'll just take these formulas for granted.